Now what I want to show you is the pH. So when you have low pH, down 0, 2, 4, you're in the acidic region. When you get to 7, which is where you see the red arrow, you are at a neutral pH. And when you go above 7, 8, 10, 12, 14, you are at a high pH, meaning more basic. So anything below 7 is more acidic in pH. I notice that pH has H there. It's talking about the concentration of acid in pH. So it's a way of discussing concentration of acid. And again, low pH is acidic, so below 7 is acidic, above 7 is basic. And notice that the equivalence of point with a hydrochloric acid, sodium hydroxide titration, and they're saying 0.1 molar or 0.2 molar, which means 0.1 moles per liter or 0.2 moles per liter. And these are very dilute. They're dilute as far as how many ions are present, but they fully ionize because they're both strong acid, strong base. So when it reaches 7, you won't see a color change if you're using phenolphthalein. But if you add one extra drop, those little blue marks with a red circle around it represent drops. If you add one extra drop, now you're in the pink, the light pink region. And notice if you add 2 drops, you're in the hot pink region. So a good titration is done very slowly when you start seeing the splashes of pink stay. So your indicators are chosen so that they change in the pH of interest. If your solution it involves a strong base and a weak acid, then the endpoint's going to be a little more basic. It won't be 7, it'll be more in the basic region, like 7, 8. If it involves a strong acid and a strong base, it is neutral. It will be pH 7. And if it involves a strong acid and a weak base, then the acid dominates and it's more in the acidic region, so below 7. So phenolphthalein's a really common one because they often do, it changes well with sodium hydroxide, weak acids. They'll also use it for hydrochloric acid when it's dilute. When you are solving a titration problem, you have to consider how many moles of acid and how many moles of base from the balanced equation. Here's a shortcut. So I'm going to show you the shortcut first in this video, and in another video I'm going to show you the long way. Many professors do not like the shortcut, but it is a very nice way to check your method at the end to make sure you didn't make any mistakes. So the shortcut method says MAVA equals MUBVUB, and then they have a little a in front, and that's how many H's are in your acid, and a little b in front, and that's how many OH's are in your base. If you only have one H in your acid, then the A is just 1. If you only have one OH in your base, then the B is just 1. The Ma is molarity of the acid, and the Va is volume of the acid. MUB is molarity of the base, and VUB is volume of the base. Again, you usually know the molarity of the base, the volume of the base you get from your titration. You read the Barrett, and you take final minus initial to get the volume of your base. You usually know the volume of the acid because you pipette it carefully, and you're solving for the molarity of your acid. So here's the first example. What is the concentration of HCl if 30 mL of 0.1 molar sodium hydroxide neutralizes 50 mL of HCl? So look at what is on your base end. They're saying for the base it's sodium hydroxide. You know it's a base because it has the hydroxide at the end. They're saying the base is 0.1 molar, so that's your MB. It's 0.1 molar. They're saying that you use 30 mL of that 0.1 molar, so that's your VB, 30 mL. And then they're saying that you use 50 mL of your acid. You recognize the acid because it has an H in front. These do only have like one H and one OH. So your A and your B, if we go back to this equation, too far. If we go back to this equation, your A is just 1 because you just have one H, and your B is just 1 because you have one OH. So you plug in the 30 mL and the 0.10 on the base side. You plug in the 50 on the acid side. So it would go in here. And again, the A and the B are just 1 and 1 because you have one H and one OH. And then you're going to solve for the MA. The molarity of the acid becomes the X. So when they ask, if they should ask, How many moles of HCl were used? This is a big reminder from chapter 13. Whenever you need moles, you take your volume in liters, so you convert the volume of acid in liters, which is 50, and you multiply it by the molarity of that thing. In this case, it's the acid. So you'd have to solve for the molarity of the acid, because you know the Va, and you know the Mb, and you know the Vb. Again, Mb is 0.10, Vb is 30 milliliters, Va is 50 milliliters, and then Ma is X. And when you solve for that, you now have the molarity of your hydrochloric acid. So that's your moles over your liters. If you multiply that by the liters of your hydrochloric acid, right now it's in milliliters, 50 milliliters, but if you took 0.050 times the molarity of your acid, you would get the moles of your acid. And your moles of base, if they said what are the moles of base at the equivalence point, you would say the same, because moles acid equal moles base at the equivalence point. So here's your hint. Convert the volume to liters always, multiply by the concentration of what they're interested in finding the moles of. In this case, it's the acid, so the Ma.